Hello, this is Paul from Foresight Tech. The objective of this lecture is going to find expression for areas using limit definition proposed by Isaac Newton. This time we're not going to just do approximation, but going to find the exact area. From the last topic, we already learned how to do approximation, right? So we use the right end point, we all use the left end point or the middle, so here. And we also find the more divide and the less area, right? And then we will move on to find the limit definition for an area. But first, we need to simplify this notation by using summation. I think somewhere I learned summation. So if we have a lot of similar patterns, so we can use this summation. The summation right in this way. Sigma, this is summation. And the term, so each term is f, right? F at x. If the general term, I use the index I. Okay, so the f at xi, and of course we have delta x. So times delta x. So I is the index. So where it goes, the index I goes from 1. So here is the beginning of I. So we wrote I go from 1 to n, right? So it goes down to n. So this means summation. Okay, means just do the summation, do the sum of all these terms. This is a general term. And when I equals 1, fx1 plus fx2 plus this is the general term. All the term is the summation. Summation is this. This is summation. Okay, and we use summation can simplify something for us to take a note. The same if we're going to take a summation notation for this, should be, this is the left end point, should be closer to this, right? Sigma. And if I use the general term is di times delta x. So this time for the index I goes to from 0, right? So we can say I this time goes from 0, okay, to the last term is m minus 1. Okay, so this is also summation. See a little bit the difference. And for the right, this is the right end point, this is left end point. We just said more divided, less area. So more precisely, so we're going to do this. We cut infinitely terms, okay, and so we will have this one. And finally, the area, we say the area under a curve. So we can use this limit definition proposed by Isaac Newton, right? M approach infinity, and the limit either I use Rn or see, and this is the right end point approximation, and we let it divide n goes to infinity, and if the limit exists, we can use this to describe what is the exact area, right? And this is the sequence. If the limit we can find for the sequence, this the area, it can define it by the limit. And the same, this is also equals this limit a or m. Okay, I mean, so no matter you use the left end point or the right point, if you take limits, they will go into the same area, the same area. If we use this summation, so Rn use this summation, what we will get? So we'll get it like this. Okay, I'll put it here. So the area could rot in this way. Is the limit m approach infinity. Rn is that. Try to be familiar with this summation. So the next topic we're going to use this. Okay, and I is from 1 to m. F xi times delta x. Okay, so this is a Rn. And what is a or n? So we also can do this. They are the same. and to take sigma I from 0 to n minus 1. This is the left-hand point, which is fxi times delta x. This is the most important. And later I will have an example show you how to use this. This we call the right-hand points, right? So you know this is right-hand point. This time is not approximation. It's not approximation because we take limits and these limits goes exactly to the area. We discussed this before, right, in the first class. If we want to find the area, or what do we need to do? We only need to find the area. So we need to do calculation. If we know f, we know xi, everything we know. Okay, so but a little bit complicated calculation later. This is the one. So we will have the right-hand point, the left-hand point. Okay, so these two, right? Do we have others? We have the middle point, and other than these three, so we have one more, which is a general, very, very important. So if we say more general, so we look at all. Okay, so I'll write it here first, and then I will draw a graph for you. The area, we also can use this to find. This take a limit. I want to look at, so what the difference I, okay, index from 1 to m, and the general term, this term no longer xi, the xi star. This is another point, dividing point. So we're going to show you later. Okay, so what is xi? I show you here. Okay, and xi star. So this is any number belongs. This belongs to the interval xi minus 1 to xi. Remember, this is the interval, right? This is a close. Means xy could be the left-hand point, or the right-hand point, or the middle point, or any other point. This is any, okay? But this is any, okay? And also I should do here. I highlighted this box. This we have an exact name, and this we call the Riemann sum. Okay, is Riemann sum. Okay, and of course the Riemann sum covers a or n, the right-hand point or the left-hand point, right? I will show you the graph so it will be easy to understand. So what does this mean? I have to show the graph here. Okay, so look at, this is x, this is y, and if I say this is a, or this time I just use x0. If this is the end point b, I use xm. Whatever, if I give it like this, okay, like this. This is the function y equals fx. Okay, so how to find the area? So remember we have we are divided by n evenly, right? So x0 per here. If I say xy is here, x2 is here, x3 is here. Okay, so I'm going to draw like this. Okay, so this x2 is this, x3 is this. I ignore, and then we go to xi minus 1 xi, okay, is like this xi minus 1, this is xi. If I'm going to ignore, go to the last second xi minus 1, these are all the point dividing points, right? Okay, so this is evening, and if we take the left point, we call it left endpoint approximation. If we take the right, we call it the right endpoint estimation or approximation, right? But this xi and how to do approximation and the Riemann sign, any xi star belongs. So we're going to pick this. So this is the Riemann sign. Okay, so I put it here. So this is describe what is the Riemann sign means. And this is the smaller rectangular area. So how to find it? Xi star I equals 1, which means between x0 and x1. I can whatever I pick. See, I pick this point. I pick this point. I means no matter where is this point I call the x1 star. This is x1 star, and then I draw a vertical line. So I find this point. This is the height of the rectangle. The rectangle, now I get the rectangle. So everyone, so you can see this is the rectangle. Where is the area? This is the area. Can we see? So this rectangle is not at the left end point, not at the right end point, even is not at the middle point, right? But however, this x1 could be any points between x0 and x1. If x1 star goes to x0, everyone remember this is the left end point. If x1 star goes to x1 is the right end point. If this goes to the middle is the middle point. Okay, so whatever any it should be like the Riemann sum. I randomly pick another one more. So look at if x2 probably I pick the middle. It's still okay. Okay, this is x2 star. Okay, if I pick this one now, see the small rectangle goes to this, right? So this is x3. x3, or probably I can pick this any. Okay, is okay. So x3 star. In this way we can draw. See, we can draw. Have you got the idea? And any point. Okay, so in here if I draw, this is the height, and then I get the rectangle. So this point I pick is I star. The last one, if I simply pick like this, okay. If this is xn star, okay, we find the height, and then this is how high. How high is the rectangle? Okay, think you can find, right? And add all the rectangle area together, so we call it the Riemann sum. Of course. So we have a longer proof. Okay, why any xi star, whatever you're going to pick, the limits are always the same. This is a big problem. We cannot prove here. It's a longer proof. So you can find it in textbook or go to Google research. I just give you a basic idea. So everyone look at this. If we take a limit n goes to infinity, do you remember what is it? Delta x. So delta x is b minus a divided by n, right? Delta x will goes to 0. Everyone, if we take a limit, this delta x will goes to 0, and this is the sum, and each term, 0 is, of course, exactly is not a 0. It's approach 0, right? So delta x, we have a name called the infinitely small value number, infinitely small. Or infinite small. Okay, this is infinite small, and so this is infinite small add, so n goes to infinity, right? So we have infinite small added together going to exact number. Okay, so that is a little bit to go out of this topic. whatever. So you can see that x goes to 0. That means the interval goes to infinitely small, right? Infinitely small means no matter, means what? It means x0, x1 will goes to touch together. x0, x1 goes to touch together. x1, x2 goes to touch together. See, because the distance goes to 0, so no matter which point you pick between this interval does not matter. Okay, so this is just a general idea. Of course, it's not proved, definitely. I summarize a little for the Riemann sum. Okay, here, remember this. So we said we have two cases, right? If I put here two cases, the Riemann sum is this. Okay, the first, if we pick xi star goes to xi minus 1 for all, okay, for all i's. This means what? And the peak xi star is goes to the left end point, right? This is the left end point. If we pick in this way, the Riemann sum goes to, or I say that the Riemann sum is exactly is the left end point approximation. Okay, the second, so if we pick this, we just discussed this, xi star is the right. Okay, we do this for, of course, for all I. In this way, if we pick the right end point, that's Riemann sum, it is goes to the right end point approximation. Okay, so I mean the Riemann sum is a general sum. Cover the left end point approximation, cover the right end point approximation, or cover the middle. Okay, or cover the middle. So if we say the middle, how do you say the middle? Is here the last. Is this? If you pick xi star is the average, means xi minus 1, the left end point, plus xi, the right end point. This is the middle, right? If for all I, in this way, the Riemann sum it goes to the middle point approximation. Okay, this is general, so very general. So Riemann sum is the most important one. And now I give you just an example. This is the so we have a different type. This is the right end point is the major one we are going to use. Okay, why? Because no matter how to pick, the Riemann sum always points to the same area. So it's easy to pick. Okay, it's better to pick the easy one, left or the right. Which one is easy? So this is easy for us to do calculation. Usually we go I from 1, starting from 1, not starting from 0. So we pick the right. This is the most important one. Let me give one example here. Use the definition means the right. Definition 2, I should here the right end point. Remember, just the right end point is what? Use this. Right end point goes from x1, not from x0. We use this limit. What the question? The questions only ask us to find the expression, okay, for the area under the graph. So, and remember, see, this is the function, right? So this is a, or we say this is what? This is x0, right? x0. This is xn, or this is. So what we can say? This time when we take a limit, so we cannot say xn. It's better this we say this is a, right? This is b. Okay. So the two end point. That means we can determine the interval is from 4 to 7. The function is this. This is complicated. How to find the area? Keep in mind that it's not going to evaluate. The next class we're going to evaluate something. But today we only find the expression. Going to practice how to use the summation. And then we do this. We just simply follow the summation, right? Remember what is the summation? We just follow the summation. All we need is find all the xi dividing point, the height, and then do the sigma, the summation, and then take a limit is the results. So the first we need to find all the xi. How to find xi? We need the increment delta x first. Delta x is this b minus a, right, over the Riemann sum, or the sum. The right and the point we take n first, and then we're going to do this 7b a 4. N is just put n here. Okay, that's 3 over n. Don't worry, later we need to take a limit that n goes to infinity. Remember, n goes to infinity, the x goes to 0. We call that infinitely small value. Okay, and then we can find out the xi. Okay, directly right. Xi, remember the definition is x0, right? Or we say is a. Okay, a plus I times delta x, or x0 plus is the same. So a is 4 plus I times this, which is 3i over n. See, we get I. So what is I? Everyone, this I goes to from 0. If I equals 0, that's 4. I is go from 0, 1, to any, right, to n, xn. Now we use the definition. What is A? So area A is this. To remember the limits, m approaching infinity, we use sigma. I from what? From 1 to n. Why? Because we go from x1, right end point, right end point. So I just wrote the formula xi, right, n times delta x. This is the formula. All we need to do is to evaluate the function at xi. We do know xi. We do know f. So just plug xi into this f function, so we can write general expression, which is this. Okay, sigma is their sigma. Okay, I from 1 to n. Fi this time goes to complex. I have to write this bracket. X square, xi is here. Okay, is this one square, right? So we put 4 plus 3i over m square, x square plus, so plus square root 1 plus 2 times x times xi times this. So I have to write 4 plus 3i over n. Okay, x square plus square root of 1 plus 2. Okay, put this, or whatever here I found is just the evaluator f at xi. It's complicated, but don't worry. Okay, oh, what is delta x? Delta x there, so I have to do this, just the times 3 over m. Okay, I cancel this. Okay, so this is delta x, this is the fxi, and we don't look at the limit. This is a summation. Okay, summation is a sequence, right? N could be changed. When n change, it goes to infinity. This is the limit. This looks very complicated, and we were talking about this how to do calculation next class. Thank you.